Hello everybody. So we continue with our first order differential equations. I remind you this looks like something y prime equals, and then we have some expression in x and y, which can be very general. And the first part we did linear, where this was a linear function in y, p. Now we're going to look at a different type of equations, which we call separable equations, equations where they can be written in the following form. hy y prime equals g of x. Now, you might protest and say, well, this is not even of the form of this is the first order, right? This is how first order looks like. But what you write down, professor, is not of that form. True. I actually, if I want to write it down in the form, in the standard form, I have to divide by h. So if I do this cross multiplying or dividing by h, whatever you call this, you see you get this expression, which is now of the form first order. So it is first order, but it is written in a special form. Now, what makes it special is this only depends on y, and this only on x. Right? There is no y's on the right hand side, no x's on the left hand side. That is what we mean with the separable. We separated the variables. So the process is called separating the variables, which is something we will talk about in the next video as well. Separating variables. And how do we solve this? Well, in fact, you actually know how to do this. In calculus, you have seen things of that. And to perhaps link it a little bit better, understanding, remember, so y prime, we often can write also dy dx. And then what were these dy dx? What kind of quantities? We call them infinitesimals. And so this was kind of a quotient of infinitesimals. It was not, we shouldn't really think of it literally as a quotient. It was really the limit of a difference quotient. Okay? But what we sometimes did was, let's use this notation here. So dy dx equals gx. I'm slightly different than what the textbook does, because I think it helps better focus on what is going on. So what I'm going to do is now pretend that this is really this dy and dx as quantities that I can multiply. So I'm going to cross multiply this and we get something like this. Okay? And what this now tells me is on the left hand side I have this derivative, or actually differential, and the right hand side the differential. The left hand one only depends on y, the right one only depends on x. So what we can do is just integrate. So if I integrate on this side, okay, and I can integrate on that side. And that's it. That's going to give us a solution. Now, perhaps this is a bit abstract. I wanted to show you what is the process we're going to do. But let's work on concrete examples. So here's the first one. Y prime equals y prime over 1 plus y squared equals x. Sorry, I should perhaps let me write it a little bit more aligned. So I hope you see that this is of the form that I claim here. What is h? So if you want to write it down here in this particular example, hy would be 1 over 1 plus y squared, right? And g of x would just be x. It's not necessary, don't use formulas too much. Just think of what is the process that I have to do. So what was the process? I said, okay, let's just pretend that this is y prime is actually a dy here, 1 plus y squared, and then we have an x dx here. Okay, so I'm using here that y prime is dy dx and bring dx to the other side if you want, thinking of it as a quotient. It's not literally a quotient, but we can manipulate it as if it is one. And now we integrate. We have to integrate this and we have to integrate this. Now, be careful, of course. What is this? Okay, let's do the simplest one first. Well, that's x squared over 2 plus a constant, right? That is the power rule. Now, what is this one? Well, it's integration, but instead of an x, the variable is now y. That's the whole point, that we have separated the variables so that this becomes now its own variable in this integration part. So we have to find the antiderivative of 1 over 1 plus y squared, or if you don't like to think of y squared, then think of 1 over 1 plus x squared. What's the antiderivative of that? Okay, so you have to look a bit in the tables of antiderivative. also all in the review sheet that I also provided. If you take here, if the function f is arctangent, that's f of x, then the derivative of that is, well, I say the tables of antiderivatives, but it's actually the table of derivatives. The derivative of arctangent is 1 over 1 plus x squared. I'm using the variable x. Okay, you have to be a bit flexible. So I want to jump a little bit from x and from y so that you comfortably can do that yourself too. So this is a table of derivatives, but tables of derivatives are also tables of antiderivatives. Just read them backwards. This is reading them as antiderivatives. So the antiderivative of 1 over 1 plus x squared is the arctangent. So arctangent, remember, is the inverse tangent, which many books and all calculators write it this way, and this is an awful notation. I cannot say, I'm not going to use it, but I cannot prohibit it because it's so widespread that what can I do about it? But the reason I find this an awful notation is because students always think that this is a reciprocal, and they say, oh, the reciprocal of tangent is cotangent. That's not what it is. So I prefer to write arctangent. Okay, so long story short, this is the arctangent of, well, be careful now, the variable is y, so I put y here. Okay? And what about the constant of integration? Well, you only need to write it on one side. And so let's write it this side. So we found here our solution. This is actually our solution. But C, so C is again a constant. I'm not going to always write this, but for now, let me, constant of integration. And remember, these constant of integrations they will be determined by initial conditions. And I'll do an example on this one later with an initial condition. Okay, that's the solution. But again, this is in implicit form because it's not solved for y. And there will be moments that we cannot do this anymore, but this is a time where we still can do it. Because arctangent is the inverse of tangent, what does that mean? This is a fancy word of saying they cancel each other out. So if I take the tangent of both sides, so then tangent of both sides, then the tangent and the arctangent will cancel out, so that will be y, and here of course there will be the tangent of x squared over 2 plus c. And so here is actually y in an implicit form. Explicit form. And that's the solution. Okay, that's the solution of all solutions. There's a little tricky thing here that we don't always know that we have all solutions. I'm going to come to that, say something about it, but very tangentially. The textbook elaborates much more on that, but I don't think this is the level of scrutiny that we need for us. It's really important just to be able to solve these things and get these solutions down. Okay, so let me do the special with initial condition now. So I do this in green, meaning it's the same question, but I add something to it. So remember, for a first order, this is just saying what is the value of y at some point. I'm going to use here y equals, okay, let's y0 equals 1. Okay, let's look this condition. So this, remember, when we have an initial condition, you only gonna try to find the constant of integration after you done all types of integration. So at this point, we should only plug things in. So I plug in 0, so x is 0 here. If I plug it in, that is 1. That's what this initial condition says. On the other side, I get tangent of 0 plus c, so tangent of c. So what is c here? Well, we need an angle that gives a tangent of 1. And what does that mean, tangent 1? That means sine is equal to cosine. This is halfway, that is pi over 4. So c is pi over 4. Now, you say, yeah, that's not the only solution. That's true, because I can add 2 pi here. So that is a little bit strange here that we get a bunch of different c's, but they all define the same function. Okay, so where c is not uniquely determined, the function, the solution is y equals tangent x squared over 2 plus pi over 4. That is this as function, whether you write pi over 4 or another value here like 9 pi over 4 would be another possibility. The function is the same. Okay, that's our first example of such let's do a few more. Let's look at y prime equals minus x over y. And I'm going to take the initial condition y1 equals 1. And I'm going to do a second one. So this is, if you want, problem A, problem B, and part C of the same problem. I'm using really the same as in the textbook here. I'll sometimes use different examples in the textbook, but this time I'm using one from the textbook. Okay, let's start this. First of all, again, it doesn't really look of this form, so we have to bring the y to the other side. Y prime is x, and then you don't have to, but I find it easier to write just the dy's, and then of course the dx goes to the other side. And now we integrate. So we integrate, that is y squared over 2. This is now just a power rule for y, right? This is the variable of integration. That is why this notation tells you what the variable of integration is. Okay? And so this is just integrating the first power, that's the power rule. And the same happens here on the other side, x squared over 2. But be careful, there is now a constant. We have to add a constant at least at one side. Doesn't matter which side, but we have to add one. Okay, that's the equation that we have. And you could say, okay, I could solve for y here, but once you're going to solve for y, you're going to have to take a square root, right? To get rid of the square. And square roots are, well, you have a positive and negative square root. So you would actually get two parts of a function. We have seen this already with circles, right? Where you have a circle, you have the upper part, which is a positive square root, and the lower part, which is a negative square root. By the way, this is, well, this looks like an equation of a circle, but it's actually an equation of a parabola. Of hyperbola, sorry, hyperbola. Okay, so in some cases like this, we say, okay, forget it. We're not going to try to solve this if we want to, but let's nonetheless, let's try. Okay, let's make so this is already, depending on what I tell you on the quiz or in what the homework tells you, you can stop at this point. But let's continue to find the solution by looking for an explicit equation. So how to do that? Well, then we have to, first of all, let's get rid of 2, so multiply both sides with 2. So that is 2c. 2c, yeah, but Professor, 2c, that's the same as c, right? It's just a constant. Okay, should we leave it? I don't know. We can leave it, we can change it in a constant d. I'm going to leave it in a constant d. Okay, and so then we see that y is the radical of x squared plus d, or the negative of that radical. So there are two branches that we say, and that is totally normal, right? I discussed this before. If you look at these fields, and in this case again, in fact, this might be the one that we did. Let's see here. Let's look at this field here. So this is minus t over y. Okay. Minus t over y. Okay. Okay, that's good. Graph direction field, and we get these circles. Okay. So. And so, for instance, we have now the initial condition. If y is 1, y1 is 1. So what would that mean here? We have to, let's use our pen, and if x is 1, y is 1. So we're talking about, sorry, yeah, this point. See, and once I pick that point, the program picks for me the curve that goes through it. So this is the part that we will get for initial condition 1. We will verify it algebraically. The other condition was at 1 we take negative 2. So negative 2 would be here, right? Okay, sorry, I cannot point, but you'll see that once I put my thing down, I'll get the right equation here. Okay, so I'm showing you these direction fields that work only for first order, by the way. We cannot do this for higher order, which we're going to deal with later. But for first order, and it's a way of kind of checking what is going on for yourself. It feels better to see what's going on. Okay, so let's do the initial condition. So the first one was y1 equals 1. So where I plug this in is 1 is equal to plus minus the radical of 1 plus d. Okay, I'm plugging in x equals 1, and that is y. Now we see that it has to be the positive, right? Because y, this is 1, it has to be positive. So it is not the negative here, we have to reject this. Okay, so 1 is equal to the radical of 1 plus d. If I square both sides, 1 is equal to 1 plus d, squaring, right? Then you get this equation, and from this I see that d is 0. So what is my solution? My solution here is y equals the positive radical of x squared, which actually is just plus 0, right? And I have the feeling that I did something wrong. What did I do wrong here? Oh, okay, I see what I did wrong. I forgot my minus sign here. This minus sign, there's a minus here. So this is a minus here, there's a minus there. So we have a minus inside, we have a minus inside. I'm sorry about that. So all this was, my minus signs were wrong. And so here we got minus 1, okay? So if I square both sides, I get this, and we see that d has to be 2. So it is, therefore the solution is, yeah, you see these little tiny different mistakes completely give different solutions in the end. So this is 2, it's 2 minus x squared. Okay, d is 2 here. But I should have written it from the beginning, so perhaps let me already do it here. We normally write some, if we know there's a minus sign, we put it in the back. But not necessary, but it is more visually attractive. Okay, so that's our solution here. We have to take the positive radical. Now, okay, let me get rid of this here, because I need my space. So this d is 2, that's what we said, right? D is 2 here. So now the other condition was y1 is equal to negative 2. So plug this in, negative, so we're going to plug this in again where? Well, here. Okay, so negative 2 is equal to plus minus the radical of d, which we don't know yet, minus, and so again we plug in 1, minus 1 squared. Okay, so this is x is 1, right, that we plug in this equation. Now we see that it's negative, so we have to do the negative here. So minus 2 is equal to minus radical d minus 1. Let's square both sides. 4 is equal to d minus 1. So we see that d is equal to 5. So our solution is y equals the negative 5 minus x squared. So the initial condition tells us when we do the implicit, we have an implicit equation, this one, which is the equation of a circle, right? If you bring the minus x squared to the other side, this is exactly how circles look like, circles centered at the origin, which the picture showed us, right? It's going to be. Now, that's in implicit equation. If you do the explicit, in other words, if you solve for y, we get two possible branches of this curve, the upper circle and the lower semicircle. And the question is, which one is it? Well, it depends on your initial condition. Okay, that's one thing that you should take from this. Okay, so, right. Next one, I do an example. Let's do this one here. Y prime equals 2xy squared. Okay, so we divide again. Y prime over y squared is 2x. Do I want an initial condition here? No, let's not do an initial condition. Okay, so we do this, and to make it a little bit more, let me write it this actually. I'm going to prepare myself for the integration part. First of all, I know for integration I should write everything in power, so I'm going to write it with a negative power. Then we have a dy, so 2x dx. So now I can integrate both sides. What is this? Well, by the power rule is the derivatives is the exponents go down, so the antiderivative exponents go up. So add 1 to the exponent, divide by that exponent, equals 2x squared over 2. Of course, the 2's cancel, and there's a plus c here. So we get minus 1 over y equals x squared plus c. And again, we can solve for y here. Cross multiplying this, you see that y is equal to minus 1 over x squared plus c. Okay. And that's a solution here. And we could again have an initial value problem and solve for this. Now, what happens here is that y cannot be 0 because we divided here. Whenever we do these divisions, so far we have not really done. If you look at the examples that we had, we had the denominator here, but it could never be 0 because it was always positive. This is the first time that we have a denominator here that could be 0, and so that means that there are solutions that, for instance, an initial condition that says that your y value has to be 0 is going to be problematic. That you cannot. So if you would say y of 1 has to be 0, you're going to have a problem here, right? Because of the original equation is minus 1 over y, which you cannot plug in 0. Okay, but these are subtleties that I don't want to talk about too much. You will never run into these things. Okay, and then let me do one more example. Okay, one more example here. I'll do this one. More because it has a little bit of an calculus problem, the integration problem. So here is this one: 1 over 2x 1 minus y squared. This is clearly a first order differential equation. It's not in the form of separable, but we can make it separable by dividing by 1 minus y squared. So we would dy over 1 minus y squared is a half x dx. I'm already prepping myself for the integration. Okay, so we have to integrate both sides. Let's do this side first. That's the easy one. That's a half x squared over 2. So there's 1/4 x squared plus constant, say. We have to add the constant here. Now, what is the antiderivative of 1 minus y squared? 1 plus y squared was arctangent, but 1 minus y squared. Now you have to go through your integration techniques of special forms, right? You had integration by parts, you had substitution, you had trig substitution, and then you had also rational functions. But that's what we are, rational functions. Rational functions, what do we do then? And this is a little bit of work, is we have to do partial fractions. So we need the partial fraction of 1 over 1 minus y squared. We will run into partial fractions later on again, and then I will review it much more in detail how to do this, but I'm going to kind of skip this, and I want you to figure out yourself that the partial fraction is actually, what does that mean? Well, it is 1 minus 1 y squared. First of all, we know that we can factor this as 1 minus y squared is actually y squared minus 1. That's the same, is y minus 1 times y plus 1. So we know that these are the two factors, and we know therefore we can always write this as a sum of two fractions which have these denominators. And in this particular case, it is 1 minus 1 here. So this, if you don't want to bother with this, just verify that this is equal to that. So I'm claiming that this is the same, right? Now, why do I... but the technique is called partial fraction, and I want you to review it yourself. We will see it later again. But what do we do now with this? Well, okay, so this integral, therefore, is the same as integrating this guy, dy, minus, there's a minus sign, this guy, dy. Oh, but that's easy, because the antiderivative of a single linear term is just the ln's. So this is ln of y minus 1, absolute value, so let's write absolute value, minus ln y plus 1. Okay, we don't have to write plus c because this is now equal, so we're going to put it equal to this part, 1 over 4 x squared plus c. Okay, now, this is an implicit form again, and the tricky part is now to make it actually explicit. The first one is using a rule of ln's, that the sum or difference of ln's corresponds to the products or different, in the case of difference, the quotient. So this is the same as ln of y minus 1. So I'm not going to write, let me not write the absolute, well, I'll write the absolute values, but I'm very happy, so to show you that it doesn't have to, I'm going to write just regular brackets here. Oops, no, that's not what I want to do. So, because to me, I'm not so much interested in the fine print here, the little fine print of what's going on exactly on these intervals. We just want to find some solutions. Okay, so we have this. So this expression on top is the same as that, except for the change that of these absolute values, right? And that is equal to 1 over 4x squared plus c. Now, how do you get rid of the ln? Ln is the inverse of exponential, so we take the we exponentiate, we take the exponential of both sides, and then get the e and the ln cancel out, so get y minus 1 over y plus 1 equals e to the 1 4x squared plus c. Okay. Now, this is still not really solved for y, so we could do that, so let's do that. So that would be, right, first of all, we have seen this before when we have our c, the constant that came from integration, right? If that gets somehow by accident or by the virtue of what happens inside an exponent, we factor it out. So you write this is ec times e 1 4x squared. We cannot do it with 1/4, right? But we can do it with the c. And then we say, okay, that is a constant. So we can change the name of the constant and call it this way. Okay, so this is where we're at. Now we have to solve for y, so we have to cross multiply again. This is d times y times e over 1 4x squared plus d times e times 1 over 4x squared. Okay, just multiply it. Bring this the y terms to one side and the x terms to the other side, so we get y minus dy e 1 4x squared equals 1. The minus 1 comes to this side, plus d e 1 4x squared. So this guy has moved here, this guy has come here, and now we'll factor out the y here. So this y 1 minus de 1 4x squared is equal to 1 plus de 1 4x squared. And then finally I divide this away and I get y is equal to 1 plus de 1 over 4x squared over 1 minus de 1 over 4x squared. Don't say that it's difficult. For you, this should not be difficult anymore. This is just standard algebra. The expressions look a little bit harder, but by now you should be comfortable in quickly doing this. Okay. Now, as I said, I'm not always going to ask you to do this in implicit form, but sometimes we do want the implicit forms. Okay. And I see that I again made a mistake. Why I keep doing this? Oh, I see. Sorry, I wrote this wrong. Sorry, I copied it wrong. Let me write it this. Sorry, I put the order in which I wrote these things wrong. So this is y squared minus 1 and this y squared 1. By the way, it's slightly different than the one in textbook. The minus sign is different, but I wanted to do it with a different minus sign. So this is what I wanted to do. The textbook does the other way around, but I want to do this way around. Okay, so we get this. Okay, and so for instance, if you now want to find initial condition, I don't know, I'm going to make up something. Let's say y0 is 4. Okay, yeah, but right, so let me not do this way. Otherwise people say, where does this come from, professor? How do you know this is y0 is 4? No, you don't. I'm going to change my problem. So this was the problem, right? Here was the thing that I was going to solve. I'm now saying I'm adding an initial condition, y0 equals 4. Okay, so let's solve this problem now with this extra thing to do, but just of course nothing else has changed so far. So we're going to plug this in other words, we plug in x equals 0 here, and then we know what y is going to become, and we can solve for d. Okay. However, as I said, you have to do it in the end. But from here where we introduced d into there, we didn't do anything except for rearranging the equations. So the same d that we use in the end equation is the same d as here. So these equations are the same. And it is sometimes easier to solve for things where it is a bit easier to solve for d here. Remember, we have to solve for d. We're going to have to solve for d. And solving d from an equation like this, you can see, can be a little bit trickier. So it's easier to solve from d. So where you normally should plug into the final equation you have, if this equation is equivalent to one simpler one, or at least from the point of view of finding d, then you can plug it in here. So instead of plugging it here, I'm going to plug it in here. So what does that give me? And so when x is 0, then y is 4, we said, right? That was the initial condition. Yeah, x is 0, y is 4. So that means that 4 minus 1 over 4 plus 1 equals d times e to the power 0. Okay, that is 3/5 equals d, and we are done. So our solution is, so now, of course, I found d using this form, but that's not the form, the final form. So now I'm using the final form and plugging the d that I found. Okay, so this is 1 plus 3/5 e 14x squared over 1 minus 3/5 e 14x squared. And that is my solution. And again, you could start looking at, you could see, try to visualize this with your direction fields. I'm leaving that up for you guys to do. Okay, that is all I want to say about this topic. And then we will, in the next topic, we will see that we start from equations that are not separable, but somehow there's a magic that makes them separable, and then we can use this technique. So keep that in mind. For the next section, you need to know how to do this part, otherwise you're lost.